6,000 feet above the moon, a yellow caution light flashed on the lunar module's display. It was a 12:02 alarm. The guidance computer was reporting an executive overflow, meaning it had more tasks queued than it could handle as the crew descended toward a cratered landing site. This tension was the result of a decade-long race that began in 1957. The launch of Sputnik 1 proved the Soviet Union could deliver a payload across intercontinental distances, creating an immediate challenge to American technological and military standing. The United States responded by creating NASA, but the Soviets maintained their lead. In 1961, Yuri Gagarin became the first person to orbit the Earth, further fueling fears of Soviet dominance in space. In response, President John F. Kennedy set a national goal for the decade: a manned lunar landing and return. It was an objective that required a total commitment of American resources to achieve. Success in the lunar race would offer proof of technological dominance. For both superpowers, landing on the moon was the final frontier required to demonstrate the superiority of their respective ideologies to the international community. Meeting Kennedy's deadline required the construction of the Saturn V, a three-stage, liquid-fueled rocket that remains the most powerful launch vehicle ever built. To lift the heavy Apollo spacecraft, the first stage utilized 5 F-1 engines. These engines produced a combined 7.5 million pounds of thrust, burning RP-1 and liquid oxygen to break Earth's gravity. The Soviet Union's competing N-1 rocket was even more complex. Lacking a single engine as powerful as the F-1, engineers clustered 30 NK-15 engines on the first stage, creating a system that required thousands of meters of high-pressure plumbing. That complexity led to disaster. On July 3, 1969, an N-1 test flight ended in a 7-kiloton explosion, one of the largest non-nuclear blasts in history. The accident destroyed the launch pad and secretly ended the Soviet Union's hopes of reaching the moon first. With the Soviets out of the race, the landing depended on the crew of Apollo 11. They were led by Neil Armstrong, a civilian commander and former test pilot known for his ability to remain calm during stressful flight conditions. Training for the mission was exhaustive. The crew spent over 400 hours per man in command module and lunar module simulators, practicing every aspect of the flight dynamics and specialized procedures for emergency situations. American victory now relied on the coordination between this massive rocket and the psychological endurance of the 3 pilots inside it. On July 16, 1969, the Saturn V executed a flawless liftoff from Kennedy Space Center. The rocket cleared the tower and pushed the crew into Earth orbit in under 12 minutes. After 3 hours in orbit, the third stage reignited for translunar injection. This maneuver increased the spacecraft's velocity to 24,000 miles per hour, breaking Earth orbit to begin the 3-day journey across the void. During transit, the astronauts performed a mid-space reconfiguration. They separated the command module, turned it 180 degrees, and used a probe and drogue system to dock with and extract the lunar module from the upper stage. While traveling 218,000 miles, command module pilot Michael Collins managed the spacecraft systems and navigation, ensuring the crew remained on course for their encounter with the moon. The flawless transit delivered the crew to the start of the mission's most dangerous sequence, the powered descent to the lunar surface. On July 20th, Armstrong and Aldrin entered the lunar module, nicknamed Eagle, and undocked for their final descent. 5 minutes into the descent burn, the computer began flashing the 12:02 and 12:01 alarms. The processor was being overloaded with data, and for the astronauts, these were unknown codes that could indicate an imminent system crash. The overload was caused by a hardware mismatch. The rendezvous radar was powered on and sending thousands of signals per second into a computer that was already struggling to manage the descent engine's flight path. In Houston, flight controllers had seconds to decide if the computer was failing. Guidance officer Steve Bales, supported by computer engineer Jack Garman, realized the machine was still processing the most important flight data. The computer's priority scheduling architecture saved the landing. It was designed at MIT to automatically shed low-priority tasks, like the radar data, allowing the processor to focus exclusively on the descent engine and flight controls. With the software actively managing the overflow, ground control issued a go command. The crew was cleared to continue their descent despite the persistent alarms. As they neared the surface, Armstrong looked out the window and saw the automated system was landing them in a field of hazardous rocks. He took manual control, flying the lander horizontally across the terrain to find a clear spot. With less than 30 seconds of fuel remaining, the engine kicked up a sheet of lunar dust. Armstrong brought the Eagle to a final touchdown in the Sea of Tranquility. Hours later, Armstrong stepped onto the moon and read from a plaque. Here, men from the planet Earth first set foot upon the moon. The crew spent 2 hours deploying scientific experiments and collecting 47 pounds of lunar samples. The combination of manual piloting and adaptive software engineering had prevented an abort, allowing the crew to complete the first lunar landing. Landing on the moon fulfilled only half of the mission's primary objective. The crew still had to return to Earth. This document outlines the separation of the lunar module's 2 stages. To leave the surface, the ascent stage ignited its engine, using the descent stage as a launch pad to return to lunar orbit. After docking with Collins and discarding the lander, the crew fired their engine to leave the moon's gravity. 3 days later, they hit the Earth's atmosphere at 25,000 miles per hour and splashed down in the Pacific Ocean. The astronauts were greeted by President Richard Nixon while inside a mobile quarantine facility. This mandatory isolation was designed to protect the Earth from any potential lunar pathogens brought back from the surface. The successful recovery marked the fulfillment of the objective set 8 years earlier. The United States had met its national goal. Apollo 11 was the culmination of a decade of work by over 400,000 people. It required the united efforts of engineers, scientists, and technicians, focused on a single, clear deadline. The program rapidly accelerated the development of modern computing and software architecture. The priority scheduling system that saved the landing became a foundation for how complex machines manage real-time tasks today. In the vacuum of space, the physical evidence of this achievement remains undisturbed. The landing gear of the Eagle still sits in the gray dust of the Sea of Tranquility. Apollo 11's legacy is the proof that even the most difficult technological deficits can be overcome. It remains a record of what human ingenuity can achieve when it is driven by a collective and unyielding resolve.